Okay, would anyone like to share what they think? Yes?
I think as beginners, they try to catch up with the masters and class A. So they work hard to reach the experience of the masters. And they get to the same point because the experience sometimes doesn't count. Is I know that, so I stop there.
Okay, so they're working harder and the masters aren't
Yes,
working
because
harder.
it's a kind of IQ against experience.
Okay,
And you get rewarded for using your brain, not for having a good one.
I see. So they're working harder. They want to catch up to the masters.
What I noticed that the results in the second were almost identical for all of them, independent of their capacity.
Yes.
For me, the conclusion was that once they were trained, they had training because they did this exercise before, now do it again. Actually, even those who are lower level catch up with the higher level. They almost they reach the same level of remembering.
But I would like to point out that they all start lower. In the previous graph, the masters could immediately place many more pieces. So that's interesting. Any other ideas out there? Yes?
Maybe the beginners with active learning and catch with the advanced.
Okay, so the beginners
Learn from the mistake from the
somehow learn.
first one.
Kind of what was said back here. The beginners kind of are learning how to place pieces. It still doesn't explain why the masters are doing worse here.
Yeah, that's the whole question.
That's the question, right? Does anyone play chess?
Yes.
Some of you? Okay. Have you ever been around a master chess player? I'll tell you the answer to this. The answer is that this is not a real game. The previous one was a real game. So if these two boards, you compare them, board 1 is a real game, and the results of that look like this. Because the master player, when they see a conceptual framework of a real game, they know where those pieces should be moved in a real game. The next game isn't real. This is not real. So they are memorizing just like the others that don't have experience. Okay? One's a real game, one isn't. This illustrates the importance of a conceptual framework. That the master chess player has a conceptual framework that the beginners don't. Let's try another one. And then we'll come back to your question. Because I'm afraid if I keep going, Jim will run out of time. So the nature of expertise is that experts organize their knowledge into a framework. I'm going to try one more example with all of you. Because sometimes the chessboard doesn't always go well with people. Let's try this one. Please try to learn the symbols associated with each of the numbers. Okay, now I'm giving you 4 numbers. What are the shapes?
6 and 4 at the
Draw the shapes next to the numbers. Can you do it?
Yes.
All right. You're the best group I've ever had then. Most people can't do it after that short period of time. Some people are like, no, I don't know. I only remember 5 as a square. That's it. Okay, how many can you do? Who can do all 4? Who can do 3? 3. Wow, okay, we're going to check his work in a minute. He must have photographic memory. Okay, 2? A couple of you? Okay. So here, you check your work. And you're like, this is an impossible task. Well, how about if I gave you a framework? Let me give you the conceptual framework for this. Does that look familiar? Okay, now you have a framework. So it's the same thing with expert learners. As scientists, you also have a framework. You can pull in science information faster than a novice learner because you've developed a conceptual framework. So the important take-home message here is that we need to help students develop that framework. And that gets at process skills of how to analyze data, designing experiments, working with reading primary literature, these kinds of things. Not just giving them the facts of science. That's very important. So I'm going to turn it over to Jim, and he's going to address the third major finding, and that is people come to the learning process with alternate conceptions, also called misconceptions. And these can be addressed with certain learning opportunities. Jim, and let me know when you want some help with the front.
Okay. So, and so what are the implications for teaching with these principles that we're using? Now, the first one I want to talk about is the fact that being an expert in a topic does not mean that you will be effective in teaching it. We've all known people who are fantastic at what they know. And then when you ask them to explain it to someone, they can't do it. Case in point. If I take a person who has never had to struggle with something, they sometimes have difficulty understanding the struggles that those who are not as, I use the word quick as they are, in understanding it. Teaching the content of a discipline without helping a learner to organize is not possible. And so one of the things that we want to be trying to do is trying to help our students organize their thinking. Because if we teach them how to organize it, then we are teaching them how to learn and how to talk about the things that they want to talk about. Now, the last one is one that I really want to drive home. Because we often hear this controversy, this discussion about which is important. There are those who talk about the fact that if I get the content right, the rest will take care of itself. And so for years and years and years, we believed that content was key. And we poured lots of money into trying to make sure that we get people with great content, and didn't get any better. There was an article in the Washington Post on Saturday which talked about the problems with, and this person was picking on biology teachers, the problem with biology in the United States. And the issue is that there's been the swing over to pedagogy. And when you talk to teachers about how can they become effective, they say, if I can learn to teach it right, they can learn it themselves. And so what we argue is that we have to have the correct mix of the content and the pedagogy. Our job as faculty members, our job as teachers, our job as mentors, is to help our students organize their own thinking in ways that will make it effective for them. Now, what we know is that we are all products of where we have been and what we have done. And so all the learning that we have is influenced by all the learning that has gone on before it. Now, we sometimes call these conceptions, as Clarissa has already said, misconceptions, preconceptions. We sometimes call them naive conceptions, in my neck of the woods. We sometimes call them student conceptions. but we're talking about alternative ways of getting there, alternative ways of thinking about something. Now, what are some common misconceptions? Young children who believe that the earth is flat. And keep in mind that there was not too long ago, in this part of the country, when I go back to Galileo, that's not that far back, where lots of people believed that the earth was flat. Because all we saw was a flat earth. Physics students who believe that when I throw something up in the air, that the force on the container persists long after the container leaves my hand. And that's why it keeps going up. Biology students who believe that even though evolution occurred in the past, it's not occurring now. Because on a scale where they, quote, cannot see it. And I guess that's why biology do a lot of work with fruit flies. Okay. And people's belief about the seasons. That the reason that it's hot in the summer is because the sun is closer to the earth. We know that's not true. That it has to do with tilt. But I've been doing too much talking. So now it's your turn. Okay. I have a track. I have two tracks. And I will place a ball on each of those tracks. And what I'm going to do is to release those balls simultaneously so that they both roll down the track. One goes along this level portion here. The other one goes down and goes along the lower portion, the lower track. And so the question that we have is, give me a click, which ball wins? Now, we're going to use clickers, and on your table, there's a clicker. Okay? And so, you all know how to use it. And so, those who believe that the ball on track A wins, pick A. Those who believe the ball on track B wins, pick B. And then those who believe that both balls reach the end of the track at the same time, pick C. Go ahead and do that.
Make sure everyone understands.
Okay, we got.
Make sure everyone understands.
How many people do we have?
About 30.
Okay, that's what I thought. Okay. I see 23. I have those who are non-committal. Now, one of the things that we know about learning is that learning is enhanced if people will first make the commitment. Because if you don't make the commitment, once the answer is revealed, you say, oh, I knew that. But once you make the commitment, you can't lie to yourself. Okay, we've got 24.
Some people are pressing.
5 times.
Make sure your clicker's on.
Yeah.
Everyone check that you have a blue
Yeah.
light.
Okay. It's 24.
And we don't know how you're voting.
No, we have no. Ah, there we go.
So it's very important everyone participates.
There you go. May not have been on. All right. Okay. We got 28. Close enough for government work. Okay.
Do you want to
Now, let's reveal the answer. And so I have a 10 who believe that the ball on track A gets there first, 7 for B, and 11 for, but both get there at the same time. Now what I'm going to do is say, turn to your neighbor just for a minute and talk about it, why you think that.
Can I close
easy.
Let's turn to your neighbor.
هي بتنزل فيها تجنبية يعني
All right. Okay. Now, thought my name. Okay. Editorialize here. What I normally do at this point in the game is have you talk about and revote to see if anything changed during the process. Okay. But what I'm going to do now, before I actually show a demonstration, I'm going to get a company to tell me why you picked the one you picked. Now, after you had your discussion, let's go over here. Somebody will know what tell me. I know there's at least one answer over there who wants to talk about it.
Please.
Go ahead.
Question?
What did you choose and why did you choose it?
I choose C.
You chose C because
Maybe depends on the kick. On the kick, on the
usually outside voice. Okay. No, okay, no, over here.
I feel like it's B, although the distance is longer, but the force of gravity or I have no idea about the physics terms. But I feel like the force of gravity will push the ball from the surface.
So we go away?
B.
B go away. Okay. All right. Last one.
Can you explain the C?
Okay, go ahead.
I mean, just clear logical question. B track is longer, or descending there will be acceleration, but it equals because going up it will lose that. So
Okay.
it will descend and
Ascend.
broadcast will equal.
Equal.
Logically,
Okay. All right. Okay. Last one.
Yeah.
Okay, go. All right. All right. Now, what I'm going to do now is actually show you the demonstration. Maestro? Okay, okay. Clarissa, can you stop it?
On the top.
Yes.
Can you stop it when it gets, okay, all right. Okay. Yeah, all right, yeah, okay. Let's take a look. Here's the physics. Balls start here. When they get to this point, the ball that goes down has accelerated due to gravity. And that acceleration due to gravity is giving it both a horizontal component of velocity and a vertical component of velocity. And so because it's doing that, the ball, from the moment they leave this point, this ball, because of going down here, when it gets to this point, it has a larger velocity in the x direction than the top ball. And so therefore, it keeps gaining distance between the two of them. Now when they get to right here, this ball starts to slow down because it is going back up the hill. But it is still going faster than that ball. And only when it gets back to the top do they both have the same velocity. Which means that the ball on track B will always get there first. But let's do one more.
Doesn't look like that in the video.
Go to the, there you go. Now, so, one more. Right now. I modified the track. And such that the only difference between this track and the previous one was that it's now a V. So there's no level part on the second track at the bottom. And it's much deeper. So same question. Does the ball on track A win? Does the ball on track B win? Or does the ball on track C do they both get at the same time? Almost the ball on track C wins. Okay? Okay? Are you ready?
They're still clicking it. Any more?
There we go. Now let's show you the result. Okay, we have a significant number who say the ball on track A wins, a significant number who says the ball on track B wins, and a few of them who say that they both get there at the same time. And now I will show you the demonstration.
Sorry, tension is palpable. It's just me. My problem, my problem. Hold on.
Okay, which one won? B. Now, what I want to say to you is that you did precisely what those students do. There is a strong perception that's built into our psyche that says that the ball that goes the furthest distance will always lose the race. And even when you are given an explanation as to why the physics works, that strong perception still drives you until you
It's logic.
yes. And I mean, there's an old story that we sometimes tell about Galileo on the Leaning Tower of Pisa. And he believed that objects fell at the same rate, regardless of their mass. And the story goes that he assembled a group of physicists to stand at the base of the tower. He went to the top and dropped a heavy ball and a light ball. And when he came back down, the story goes that so strong was the perception that the heavier object drops faster. That when he came back down and asked what they had seen, they still said the heavier object got there first. Now, there are those historians who say that's a false story, but it makes a good story in a way. I can't vouch for its authenticity. So, let's go back and take a look at it.
Do you want me to play this?
Play this again. Now notice, as soon as that ball leaves this point, now that's going to slightly ahead. Look, and by the time we get down here, this one is clearly ahead. And even though it's going up the hill, note that it is still maintaining a significant separation. Only when it gets back here, at the top, are they finally beginning to travel at the same speed in the x direction. But it is already so far ahead, so therefore it never does what? It never catches up. Okay, now, we'll go back and tell you what happened on the very first one.
Excuse me. The speed here between the first when we're falling down, accelerating, okay, and when going up, steady. Well, is that equal?
One more time.
Because when it goes down, it should go up, and probably because of the distance between going down and going up is the same.
Okay.
So they lost the difference. They lost the difference in the speed.
Right.
So that's why they became almost the same. And
Well,
so-
yeah. Well, what happened on the first one
Yeah.
was that in that set of videos,
Yeah.
there are those where the motion has been slowed down. And so therefore I can't neglect the frictional effects. And if I don't neglect the frictional effects, then I get some things that we don't, that we have to give a different explanation thereof. Because it's not only just, I mean, what I'm assuming here, that this is motion without friction. Now there is friction there, but because of the setup, it's negligible.
No, I'm just asking because of the physics.
Right.
If, for example, going up is longer, the distance to go up is longer than the distance going down, would it be the same?
Oh, same, the same. Because the issue is this. As long as these two tracks meet at the same point, it doesn't matter when I make this deep, as long as I don't make it so deep that it is no longer rolling without slipping. Because if it starts to roll without slipping, then there are other factors that go in. But the assumption is that I can make these balls roll without slipping or sliding. If I make this too deep, then I get slipping and sliding, and then there are other physical effects that go in here. But as long as I can set this up so that these balls are rolling without slipping and sliding, then I don't have a problem. Okay, what I'm going to say is that what's going on here is that as soon as they leave here, these balls are traveling, when they get to this point, they both have the same velocity in the x direction. Forget the y direction because it doesn't matter. Now, as soon as this ball leaves here, the ball going along the bottom track is now going faster and faster and faster. This one no longer changes its velocity because it's moving what? Only horizontal. I'm assuming no friction, so it doesn't slow down. When it gets to the bottom, this ball now starts to go up. And as it starts going up, it is slowing down because of gravity. Okay? But even though it's slowing down, it is still going faster than the ball on top. Only when this ball gets back to this point will they have the same velocity in the x direction. But by that time, the race is what? It's over. Yes.
The issue here is that our responsibility of match is because we try to solve this problem out of your logic,
Yes.
not because of physics.
No.
So logically, we have the same distance, you can have let's say acceleration here, which is equal by
Yes.
more incompetency. So we by logic try to.
But well, I would argue, I still use logic,
Yeah.
but there's something faulty about the logic you use.
Yeah, that's
That's
so
the
physics
alternate
logic.
conception.
Yes, your ultimate conception, your misconception. There's a strong misconception that the further something goes, it must take longer. Now moving on.